This is the Proton Guru video practice for topic 1.17 through 18, determining chirality and assigning absolute configurations, that is, assigning the R and S labels. Some brief and straightforward reading to get you ready for the type of problems we'll cover in this video can be found in the Organic Chemistry 1 Primer 2018, and you can also find a bunch of other organic chemistry videos and information on how to match those videos up with your particular course's textbook to help you in your course at protonguru.com. One important skill is to be able to identify stereogenic carbons, and this question asks you how many stereogenic carbons are present in morphine. Well, although this is a very complicated structure, the rule for identifying stereogenic carbon atoms or chiral centers is pretty straightforward. You just need to identify any carbon atom having 4 different groups attached to it. So any of these doubly bound carbons wouldn't be able to be a stereogenic center because it only has 3 things attached to it: carbon, carbon, hydrogens. You also can't have a stereocenter where you have 2 things that are the same. So this has 2 hydrogens that are the same as each other. That can't be a stereocenter. So let's check the other carbons that aren't as easily ruled out. We have this carbon, which has a hydrogen not drawn in the line bond structure. It's got a nitrogen, it's got a CH2, and it's got a CH carbon-carbon. So that's 4 different groups attached to that unit. So that is one stereocenter right there. We'll check this carbon. It's attached to this quaternary carbon, this carbon with a nitrogen, a hydrogen, and this doubly bound carbon. So 4 different things attached to that carbon as well. Well, let's see. There's this carbon in the front with 2 H's. That can't be a stereocenter. This one also has 2 H's. That's not a stereocenter. How about this one? It's got this double bonded carbon at the top, a carbon with an oxygen on it down here, a carbon with another carbon on it over here, and this carbon that links up to the nitrogen eventually over here. So those are also 4 different things if you count out from that center far enough. So that's a stereocenter. And how about this carbon right here? This carbon has the alcohol carbon attached to it, it's got the O attached to it, it's got a hydrogen that's not drawn, and then this other carbon. So that is also a stereocenter. Finally, we have this carbon with the OH attached to it. There's a hydrogen on a wedge that's not drawn. Then you have a double bonded carbon, and then this other chiral center up here. So this carbon is also a stereocenter. So it looks like we have 5 stereocenters in morphine. Well, let's do the same analysis for strychnine, another natural product derived from plants. We have to look for any carbon having 4 different groups attached to it. So we can rule out anything that's a CH2. So those are all CH2s there. Here's another CH2, another CH2. We can rule out carbons that have double bonds, as we did in the previous problem. So let's more carefully check the other carbons in the structure. So we have this carbon here, for example. It's got a hydrogen, it's got this tertiary carbon, it's got this carbon which has a nitrogen on it, it's got this carbon which has an oxygen on it. So those are 4 different things. So you see, if it's carbon initially tying, you look one further out and see the next atom to see it's eventually a different group. So that's a chiral center. And the same thing for this one. There's a hydrogen that's not drawn in the line bond structure. There's this oxygen. And there's this carbon that's a secondary carbon, and this carbon that's a tertiary carbon. So now we have a chirality center here as well. This carbon has a double bond, can't be chiral. This carbon has a nitrogen attached. It's got a hydrogen, this tertiary carbon, and this quaternary carbon. So definitely 4 different things there. This carbon has the arene attached to one side, this carbon with a nitrogen down here, this carbon with a different nitrogen here. This nitrogen is part of an amide functional group, but if I look up here, this nitrogen is part of an amine. So those are different groups. So this is a chirality center as well, a stereocenter. I have a couple more carbons to check here. Here's one that has a nitrogen on it, quaternary carbon, the secondary carbon, and a hydrogen that's not drawn. So that is also a stereogenic carbon. Finally, I think the last one we have to check is right here, and we see it has this doubly bound carbon over here. It's got this secondary carbon here, this tertiary carbon here, and something not drawn is the hydrogen. So we have a stereocenter there as well. Another really common type of question is one that asks you which molecules will rotate plane polarized light. Well, if you did the reading in primer lesson 1.17, you know that only chiral molecules rotate plane polarized light, so this is really just a different way to ask you whether a molecule is chiral. So when you're looking to see whether a molecule is chiral, you look for 2 different things. First, a chiral molecule must of course have chiral centers, which seems relatively obvious, but this one, for example, has 2 methyl groups here. This is not a chirality center, so this can't be a chiral molecule. This one is symmetric here, meaning that this substituent and this substituent coming off the carbon are the same all the way around the ring until they meet up. That means that this also does not have a chirality center. And it has symmetry anyway, which is the second requirement. A chiral molecule does not have symmetry. So the molecules that you find that are symmetric cannot be chiral molecules, even if they have chirality center. So you look for symmetry. A lot of people are fooled by this one and think it looks kind of symmetric, but this and this are not the same, so that's not symmetric even visually. This one, though, is symmetric because these point the same way. So that's an important differentiating feature. This one's symmetric. This one is symmetric and has no chirality centers. This one has no chirality centers. If you look at the other ones, we see chirality centers here, 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 and here, and they don't possess any planes of symmetry. So there's no chirality center here, does not rotate plane polarized light. These are symmetric, they do not rotate plane polarized light. The ones that do rotate plane polarized light, the ones that are chiral, are the ones we have here. The next question shows us the same molecules and asks which molecules are optically active. Well, this is almost a trick question in this context because optically active means that they rotate plane polarized light, so this is really asking the same question we just addressed. Again, another way to ask if something's chiral. So this is not going to be optically active, neither are the symmetric molecules. So the ones that are optically active will be the same ones that we just identified as being those that rotate plane polarized light, those which are chiral. Okay, so now being able to identify when a molecule is chiral, the next thing we need to be able to do is to provide IUPAC names for chiral molecules, including the label of configuration, assigning R or S to specific structures. So if we take a look at this structure, first thing we have to do is to assemble the regular name of this compound without the R or S label. And we made a nice video about this for Proton Guru video practice 1.14 if you need review on how to name the structures. So the base structure is called 5-chloro-2-pentanol. And now it's time to assign an R or S label. So the procedure you need to follow to do that is first draw in the missing hydrogen on the stereogenic carbon, and then you need to assign the priorities using the Kahn-Ingold pre-log rules for all those groups that are attached to the chiral carbon. So here's our chirality center. The oxygen group is number 1, the longer chain is the second highest priority, the methyl group is the third priority, and the hydrogen is the fourth last priority. Now when you assign the R or S label, it's important where that fourth priority group is. That's what you look for first. Here the fourth priority group is in the back. If your fourth priority group is already pointed away from you, you just count from 1 to 2 to 3, the first priority to second priority to third priority, and see if that progression is clockwise, and if it is, you have the R configuration, or counterclockwise, which would indicate an S configuration. A really important point here is that you've got to ignore that fourth priority completely. You can even scribble that out. You only count the progression from 1 to 2 to 3. You don't care where that fourth priority group is pointing with respect to those. So you go 1 to 2 to 3. That's a counterclockwise. If you're turning a steering wheel that way, you go on a left-hand turn, and that's the S configuration. So the proper full name for this compound would be S-5-chloro-2-pentanol. Let's take a look at another case. We have this relatively simple alkyl halide. We start off by assembling the name without the label of configuration. It's some sort of 2-bromohexane. And now we go to assign the RS label. We again have to fill in that missing hydrogen and assign the priorities. If we do that, we see that now the fourth priority group is in the front. Well, this is backwards of what we consider ideal. If it's in the back, you just count 1, 2, 3. But if the fourth priority is in the back, this is backwards of ideal, so we count backwards as well. You just have to count 3, 2, 1 and see whether that progression is clockwise or counterclockwise. Again, we ignore that fourth priority substituent completely. Scribble that out, and we're going to count 3 to 2 to 1. If we do that, 3, 2, 1, that progresses in the clockwise direction. So you'd add R to bromohexane. So here's another example of this type. What is the absolute configuration of this molecule? We're not asked to provide the whole name, just whether this is R or S. So now we just have to assign the priorities. We don't need to provide a base structural name. Bromine has the highest atomic number, then chlorine, and then we have a longer carbon chain versus the shorter carbon chain, a methyl versus a primary carbon. Well, this brings up a problem. The fourth priority group is in the plane of the screen, so we need to reorient the molecule. We can't count forwards 1, 2, 3 or backwards 3, 2, 1 if that lowest priority substituent is in the plane of the screen. We have to reorient the molecule. One method to do that is to hold this bond steady, rotate around it. And this is pretty easy to see if you use a model kit, but all we're doing is spinning this sort of propeller of these three substituents around. So I'm rotating the chlorine up to where the methyl group is, the methyl group down to where the bromine is, and the bromine over to where the chlorine is. If you do that, you'll get this conformation, and now your fourth priority substituent is in the back. Once you've positioned that fourth priority substituent in the back, you can then ignore it and count 1 to 2 to 3, and see that this is in the absolute configuration of S. Now, one of the most challenging types of questions that people face in stereochemistry is trying to figure out how to assign R or S labels to molecules that are drawn as Newman projections. And this requires some visualization of the three-dimensional shape of this material. So let's use a little imagination. So imagine you're looking at the Newman projection from this side where I've drawn this very creatively drawn person. Now, if you're looking at the Newman projection from this side, the front of the projection is on your right. This is your right hand that's coming out towards us in the screen. If your right hand is grabbing onto this hydrogen, that's on the front of the Newman projection. It's part of this part highlighted in blue. Your left hand is grabbing the back side of the Newman projection. So when you draw this, this is the right side, this is the left side from the perspective of this person looking at the Newman projection. So I know to draw my line bond structure out where that group is on the right and that group is on the left. We also see that your hands are grabbing these hydrogen atoms, so they're pointing towards you. So you're grabbing the hydrogen atom on the front of the molecule. This hydrogen is pointed down, it's pointed towards you. This hydrogen atom is up, and it's also towards you. There's also a hydrogen atom away from you over here, and the CH3 is pointed way away from you. So that's how you know how to fill in the hashes and the wedge lines. Now we can go ahead and assign the configuration of that site. We have to prioritize. 1, 2 would be this ethyl group over here. 3 is this methyl group, and your fourth priority is H. Well, your fourth priority is in the front, so we need to count 3 to 2 to 1. We count backwards because the molecule is oriented backwards of what would be what we call the ideal. So 3 to 2 to 1, that would be the R configuration.